Hi, I'm Keaton Blair, and I'm here to talk about the wavelet transformation and how we're using it in our atmospheric research. I spent the past summer working with the Montana Space Grant Consortium under the University of Montana Borealis program. With funding from NASA and the National Science Foundation, we were fortunate enough to be able to travel to Villarrica, Chile this past December for the total solar eclipse. After traveling to South America, we launched 50 weather balloons, one balloon every hour, launching balloons all day and all night for 50 hours. And we even got to see one very wet, cloudy eclipse, as you can see right here. Now, in this presentation, I'm going to cover why we did this, what we're hoping to find, and then walk through some of the cool math involved in our analysis. So the goal of our study is to learn more about internal atmospheric gravity waves. What are gravity waves? While they sound similar, these are not the same thing as Einstein's gravitational waves. Gravity waves are very similar to familiar oceanic surface waves, but they propagate inside a fluid rather than on the surface. When any fluid, such as air or water, becomes stably stratified, energy can propagate as waves along the boundary between the two layers, much the same way that energy propagates as waves along the boundary between air and water. We call these waves, when they're inside and not on the surface, gravity waves. Now, these waves are very common in the Earth's atmosphere. This image shows waves being generated by mountain topography, but other common sources include convection and wind shear. Gravity waves play a role in the distribution of energy throughout our atmosphere, but they are not entirely understood. The goal of this study is to confirm theoretical predictions that solar eclipse could generate gravity waves, increasing our understanding of the phenomena and hopefully leading to more accurate weather and climate prediction models in the future. Since gravity waves, unlike water surface waves, aren't usually visible, we need to take atmospheric measurements in order to detect them. We do this using radiosondes. The instruments that we call radiosondes are popular among atmospheric scientists because they're small, portable, and accurate. The radiosondes that we use during our study, depicted here, are the GRA DFM-17 radiosondes. Now, in our research, we connect the radiosondes to a parachute and weather balloon. When we launch the radiosondes, they rise up through the atmosphere underneath the balloon. However, when they encounter a gravity wave, they're affected in much the same way that a piece of driftwood might be affected on the surface of the ocean. This means that when we look at our wind speed data gathered by the radiosonde, we can see gravity waves as ellipses in our data. However, it's not quite that easy. When we actually look at our raw wind speed data, it looks messy and it's hard to immediately identify the presence of waves. In order to do so, we have two main methods. The first method, called the hodograph method, involves searching the data manually and with the help of algorithms for shapes that appear ellipse compatible. Then, a best fit ellipse is found for the data points using the least squares method. That ellipse is then analyzed to determine the physical wave characteristics such as wavelength and phase speed. The other method, which I will explain in detail, is the wavelet method. Now, the first step in this process is to wavelet transform the data. A wavelet is a wave that, unlike a sine or cosine, which continues forever, is localized in time. There are many wavelets, however, we use the Morley wavelet because of its physical resemblance to gravity waves. As you can see from the equation on the right, the Morley wavelet is a sinusoid that has its amplitude modulated by a Gaussian function, so that the amplitude of the waves follow a normal distribution. In order to perform the wavelet transform, we do what's called a convolution of the wavelet with our data. And we do this for a number of what are called wavelet scales, denoted as S, and time steps N. Now, the wavelet scales correspond to the frequency and vertical wavelength of the gravity waves that we're looking for, while the time steps are simply each original data measurement in our data. To do this convolution, we scale the wavelet so that it's centered at the time N and scaled by the wavelet scale S. And then we take the product and sum across all of our time. We can see this in action here. On the left, we have the process of the wavelet transformation, and on the right, we have the outcome. You can see on the left that we're shifting in scales. So for every wavelet scale S, we iterate across all of the time steps, centering the wavelet at that time step. Then we perform the convolution, which is the product and the sum, written here as a continuous integral, but performed in our code and for our research as a discrete sum. Now, the result of this is, on the right, a three-dimensional surface that has axes of wavelet scale and time, and the height of the vertical surface actually measures the similarity of our data to the Morley wavelet. When we apply this to our radiosonde data, we get what we call a power surface. And once we've done so, the potential waves show up as local maxima in the power surface as points of high similarity between a Morley wavelet with that specific altitude and that specific wavelength. And this allows us to separate waves which may appear similar in our original data, such as the waves highlighted here, which have very similar altitudes, but very different wavelengths. We can then reconstruct the time series at specific altitudes and, more importantly, at the specific vertical wavelengths of the waves that we're looking for. This allows us to see neat ellipse-like structures in our data rather than the mess that we originally had, because all of the wavelengths present in our data that weren't part of the wave were also included when we trimmed out a specific time. Finally, this allows us to get the actual physical wave characteristics from the data. We do this by applying what are called the Stokes parameters, which is a name for a collection of equations derived from the general physics of wave behavior. And using our reconstructed time series, we can find anything we want to know about our waves. So for every radiosonde flight, we can create a file showing a list of all the waves that we detected and any of their properties. Then we can use these files for further analysis, which we do in trying to determine what the wave source are and looking for changes in the gravity waves present across a time, for example, the 2 days before and after a solar eclipse. Now, an example of this analysis is this plot, which depicts waves measured during the summer before we traveled to Chile. On this plot, each gravity wave is represented as an arrow, where the direction of the arrow corresponds to the direction of propagation of the gravity wave, and the length of the arrow corresponds to its intrinsic velocity. We're currently in the middle of analyzing and verifying our solar eclipse data that we measured in Chile. And once we feel confident about our results, we're going to submit them for publication in an academic journal. Looking further into the future, there are a number of things that we want to investigate and ways that we think we can improve this method that are listed here. And even further beyond that, we've already started planning for eclipses in 2023 and 2024. And we have a lot of ambitious ideas and high hopes, and we're really excited about that. So thank you so much for watching. I hope that you learned something. If you want to know more about us and what we're doing and what we're planning on for the future, visit the Montana Space Grant Consortium website for more information. Thank you.